Hello, everyone. It's my pleasure to welcome you to the Cybersecurity Track. It's nice to see so many people here. I won't waste any more time. Our first speaker will be Francesco Pavanello.
Hi everyone, my name is Francesco, and today I want to show you how it is possible to improve the corporate security only using open source software and data, trying to impersonate an attacker and his point of view. And this process is known as exposure assessment. So after briefly introduce myself, I will give you a bit of context in order to make you better understand what I will talk about. And then we will go through the main topic that is, of course, exposure assessment. And in conclusion, I want to show you some tools that you can try if you want to perform this process by your own. So, even if people often ask me if I am allowed to drink alcohol, I'm 25. And I recently concluded my master's degree in cybersecurity. And I'm now working as a cyber threat intelligence engineer at Wood Phoenix here in Bolzano. These are my contacts if you want to reach me out in the future. So, what you can see here is known as a cyber kill chain, and it represents a general overview of the various stages of an attack. And it starts with the reconnaissance phase, during which the attacker gains knowledge about its target, in order to then be able to create, in the second stage, a specific attack for the target. Then it delivers the attack, usually, for example, using a phishing email. And then he waits until the victim will download the malicious code and execute it on its machine in order to gain access to that machine and then have the control and the ability to perform whatever he wants. An exposure assessment, as you can maybe think, is placed in the reconnaissance phase, and it tries to replicate this attacker activity of acquiring knowledge about the victim. This is probably the most important phase because if he is able to acquire enough knowledge, he then can go through the developing of an attack that is successful. As I mentioned before, we want to do it using only data that are publicly available or tools that are also publicly available. And this is the definition of a branch of the intelligence known as OSINT, or open source intelligence. And as you can see, there are different sources that we can go through to find the data that we need. For example, also newspaper, government, or public document, radio, or television transmission. But since we are talking about cybersecurity, we will focus on internet, the surface web, as well as the deep and dark one. How we can find what we are looking for? Basically, we can use some Google Docs to specifically find some data, or as I said before, there exist a lot of open source tools and programming libraries that let you develop a script that then gathers all the data that you are looking for. Furthermore, there exist some services that deliver this information via their API. Most of them are also free of usage. And the link there are some more information about what is the OSINT framework. The last one is a repository that we started some years ago. And now, thanks to the community, here you can find a lot of Onion sites, Telegram channels, or other channels where people, most attacks, share information about what they do, and data breach and so on. So, what is an exposure assessment? Usually, the starting point is a domain, the target domain. And here, with this domain, you can then, for example, using DNS query, you can find the hostname that are related to this domain, or the IP addresses these hostname are resolved. Or maybe with website crawling or crafting the email addresses, knowing the employees' names and surname and the format of the email of the company, you can create a lot of emails. Then, of course, you need to go more in depth. So you can search, for example, for open port in order to determine which of these hosts and machines are still active, and discovering what kind of service they are exposing, and if any of the technology involved suffers of any known vulnerability, and if there exists any exploit related to this vulnerability. Or if you consider email address, you can search this email inside the data breach in order to find corporate credential. Or if they are registered to some specific social network, you can search for this specific data breach if it exists, and then maybe use the credential you find to create a dictionary attack. But this is not, the domain is not the only starting point. You can also start from keywords, and this is especially useful if you want to scrape and search information inside the deep and dark web. Here you can find content related to the company, on maybe social network, or more important, on Onion marketplace, where attackers usually sell what they leak. Important in this context is what a stealer malware is able to download from your browser. So all the credentials that you save, all the autofills and so on, are downloaded and then resell on these marketplaces. Also, you can find if your victim was previously compromised by the ransomware on a ransomware gang website. And here maybe they also share a proof of what they exfiltrate. So these are also useful information. So as you can see, there are also others data that you can retrieve from internet. For example, you can find files that contains sensitive data publicly indexed on Google, or you can check if there is any misconfiguration with the mail server. For example, checking if the SPF or DMARC record are correctly configured, or if the HTTPS protocol is properly configured. Or if another important thing to search for are phishing domain that maybe could be already registered, and so maybe already in use. And you can do such operation, creating a list of typo squatting domains starting from the original one, and then check if there is any DNS record related to this malicious domain. Often they are also maybe legitimate domains that changing a letter is about for another company. And finally, in where I brought here Python scraper and libraries, these are useful libraries that you can use if you want to develop your own scraper. I think that's all for my side, and we have a few minutes left, so if you have any question. Yes?
Just a second, we'll give you a microphone.
From my understanding, you are working in the cyber threat intelligence, you have a cyber threat intelligence job. How do you communicate your findings to the Security Operations Center team and to other key people in your company?
Usually,
or what type of finding do you usually communicate?
Okay, no, everything that I show you is something that we look for. So then we create IOC and give these IOC, so IOC are index of compromise, to our Security Operations Center. And then the Security Operations Center analyze the IOC, and the analyst create a ticket for our client where they described all what they found related to this finding. And then the final client know how to mitigate and what was about the finding.
Are
there any other questions? One more?
Yeah, this is a very interesting topic for me, so I may have a lot of questions. And do you use any kind of open source platform to collect and categorize these kind of IOCs, or to cross-link these IOCs with other maybe private threat intelligence feeds?
Yeah, for example, there exists OpenCTI, that is a powerful platform, open source, that you can configure, create a lot of connector, and using this connector you can import a lot of data from different sources. There is a connector also with Elasticsearch, and so then this is the channel through which we communicate from our point of view to the SOC.
We still have some time. Are there any other questions?
Another question. I have seen that you also mentioned social networks, so maybe Telegram chats or Mastodon or whatever the threat actor uses, to exchange information. How do you? What kind of keywords, do you use to not be submerged by a lot of false positives?
Okay, usually we use general keyword for the scraping phase in order to download a lot of stuff that maybe can be a false positive. Usually most of them is false positive. And then offline, So in order to obfuscate what we are really looking for, we perform more in-depth analysis, for example, using the complete domain of the target company, or CEO name, or other management name. And in that way, we are able to filter out everything that is not related to our target, to our client. And then we are able to also obfuscate what we are looking for in order to not leave any hint on the internet.
Okay. Thank you very much, Francesco, for your talk.
Thank you.
Also, thanks to the audience for the very good questions. We will have a short break and then we'll be back. Thank you. So welcome back, everyone, to our cybersecurity track. Our next speaker is Carlos Esteban Bude.
So, hello everybody. Is this working? Yes, and it went too far. I am Carlos Bude. I am assistant professor in the University of Trento, and now I'm going to talk a little bit about how could we predict security vulnerabilities, it should be. That was not a happy choice of words, but it's about vulnerabilities, just so you know. Anyway, why in SFSCon? Why about free software? Well, let me be just lazy and Google for most popular software programs, and we see a lot of programs listed there, and we know that at least half of them are free software. Not from the Free Software Foundation, that's an unhappy choice of icon, but it's free source software anyway. So what happens with the other half that is shown over there? Well, they actually use free software in the full chain, one way or another. So the picture, the amount of software that we know that is open source and it's free and it's being used out there in the wild, in our phones, in this screen, in our computers, it's too large. It's too large even to fit on a screen. It's essentially a very large picture. So free open source software is something that is pervasive. At this point, I think that's something that is very happy. It's a nice outcome, a nice actual current state of affairs. At the same time, we know that software has bugs, and some of those bugs are vulnerabilities, right? So in particular, many of these are being published, and are being searched for systematically and published. So they are at least in one of the databases that exist, assigned a specific ID. They are called CVEs, for Common Vulnerability Enumeration. And this is public data that exists in the wild and is being fed and increases as database every day, every year. You see a plot here from the American corporations, but also other studies show that, well, first of all, the blue bars there, there's a little typo, sorry, on the x-axis. The last two entries should be 2021, 2022. Anyway, I was saying, the blue bars here show the amount of free software that is being used by surveys that have been done by Black Duck and Synopsys. So you see that it's essentially 100%. So if you're using software, there's almost 100% chance that some of it is going to be free open source software. And at the same time, if you look at the magenta bars, you see that at least one, it's very likely that many of those libraries that you are using, of that software that you are using, is going to have one vulnerability. So one of these bugs that an attacker can find and exploit to its own advantage. And also, alarmingly, you see the green bars that show that also it's very high, the amount of very high severity vulnerabilities. So it's not just something that can make the program crash. Maybe it's something that can spill my data, okay? So if we multiply the amount of vulnerabilities that are there with the amount of libraries which can be attacked by that, well, you know, we are essentially playing Minesweeper. And if we touch one of those, everything falls, okay? So maybe I'm talking too much statistics. You are here for coding, you like code, so let me show you some actual code in the screen. This is essentially dependency tree of the Redison library, Java library that you can download in Maven and use for your own purposes. And Maven has a nice command which shows you the full dependency tree that we see down there. And of course, if we are using these dependencies, it means that when my program is executing, at some point the program counter is going to be pointing at the code of one of these libraries. This means that if there is a vulnerability in one of those libraries, I'm going to execute that code, and that's how I am being hit by that vulnerability, right? I am not the owner, perhaps, of that dependency, of that library, so I cannot modify that code, but if that code is vulnerable, and I am using it, I am vulnerable, right? Repeat for every single dependency that we have there. So if we are using many libraries, which usually we are, then any vulnerability in there is going to be able to potentially, vulnerate ourselves. So they are a potential risk, which looks like a lot of bullets to stop. Now, what if I told you that you cannot necessarily stop the bullets, but you can just not be there when they are going to hit in the first place. So just blue pill the thing. Well, the idea is not so strange if you start looking at the software development lifecycle and how vulnerabilities kick in into this development. Essentially, let's say I am the owner of Redison, or I am a developer there in the company that produces Redison and puts it into the wild, and I am using a dependency. This dependency in this case is NT Core, but let's say that I have only one version of that code available. Then which version I am going to use? The only one available, not my choice. But when there is a second version and I want to release an update of my own code, then I have a choice there. I can go to the latest code, which maybe is nice, maybe is more secure, or maybe not, and I just become conservative and remain there using the previous version. And so on and so forth. At some point, I'm going to perhaps be interested in actually adopting the new dependency when I release my own new version. And this essentially repeats. And usually, as far as I understand at least, companies have certain policies on how to do this more or less systematically. Perhaps some requirements arise which kind of change the pattern, but here we do see a clear pattern for Redison. So we have two versions of the library which are using essentially the same dependency. Then we change to the latest available code, all right? So that's what happens there. But then at some point, well, you know, that happens and a vulnerability is discovered, and this vulnerability affects certain dependencies. And well, unlucky us, in this case, this is all true, by the way, this is all data scraped by a colleague. Yeah, it may be that the version of the dependency that I am using is vulnerable, in which case, if the vulnerability is problematic, I will have to probably update to the latest version. And you see there that in this case, fine, I just update as fast as I can, but the pattern changes. So we have essentially a forced move, which can disrupt the production cycle of my company, and saying it clearly, it just costs money. And maybe it can also be very much insecure, like in Log4j or Heartbleed back in the day. But essentially, the question would be, okay, all right, when I am releasing a new version and I am deciding to adopt a new version of the dependencies that I have, is there a best choice that I have? Is there a best time to choose these updates and to factor them into my code? So to answer this question, one approach that we are taking now is to fit the times it takes from the release of a library until the potential discovery of a vulnerability, specifically a CVE, that is published for it. So how does this look like? It's essentially data fitting. So what we are interested in learning or fitting is the time period between the release of the library, perhaps the one that introduced the vulnerability, and the publication of the CVE that makes that vulnerability, well, public, right? And very open to the public. So this will happen for every single vulnerability that it exists and is being published in CVE. If it's a vulnerability, it affects a specific version or versions of the code. So we can measure the time between the release of that version and the publication of the CVE, and so on and so forth, in the hope that we can fit some PDF, some probability density function that estimates the expected time for the release of a vulnerability from the deployment of the version that essentially introduced it. So what the plot shows over there is the probability as a function of time that a CVE is released from the point at which a dependency was updated. And this gives us some quantitative information, some rule of thumb, some best guess on, is it time to update my dependency? I am going to have a new release now. Am I in the peak of the probability? Is it likely that the version that I am using now is going to be discovered vulnerable and a CVE is going to be released for it? This is the core of it, but there are some details to take into account. First of all, vulnerabilities are not a very common thing. So there is a lot of software out there, and there are a lot of versions, and every now and then a vulnerability is found for some of them. If you measure the amount of vulnerabilities versus the amount of versions of code, these are really rare events. So how can we learn something from such scarce data? Well, essentially just group them together. Aggregate, use many vulnerabilities to learn for specific libraries, which is the the time of expected release of a CVE for it. In kind of the opposite direction, we know that different libraries have different purposes, and perhaps certain vulnerabilities are very specific to the type of library that is being used there. So this kind of goes really in the opposite direction, because it says don't put everything in a bag and learn from it. It could be better to actually distinguish the different type of libraries that there are, or maybe the different type of vulnerabilities that are out there, and then learn from these different clusters differently. So essentially, we need to strike a balance that identifies relevant features for security vulnerabilities and then clusterizes to some approach my data points for fitting. So if I am looking at the full amount of vulnerabilities, each dot in that little place would be a library version, which is vulnerable to some CVE. So let's plot that versus some metrics that or some features that I think are relevant for security purposes, right? So we clusterize that, or we, in this case, just divide it by certain quadrants, and for each individual quadrant, we learn an individual PDF, because we expect them to behave similarly in each quadrant in terms of the vulnerability releases. Notice, however, that this division is not to learn the vulnerabilities itself. It's only just to divide the learning points, and then we learn by fitting the PDF. Okay? So we have done this already. Please notice the first word of the title of the slide. So this is not very, very polished stuff. I'm showing it because I think it's nice. We divided libraries based on essentially their size, measured in number of lines of code, which has a lot of caveats, but so be it. And also we divided libraries by whether they were intended to be used in the internet, which we decided through a decision process, something that we did actually ourselves in-house, or not, or if they are possibly intended to be used inside of a computer for local use. And this data that we fitted is from Java libraries in Maven, so published software. And yeah, we observed that the curves that we have learned for each of the quadrants are effectively different. And the nice part is also that we observe a difference between, for instance, the sizes. So you see that each quadrant has certain patterns there. Here, these two have a more steep spike, and they have a more skewness to the left, meaning, in a sense, CVEs are released faster for them. Well, yeah. I'm not going to delve too much, time is running out, but that's essentially what we have been doing in this past time. What is left now for us to do forward is choose more proficiently the features that we use for this clusterization, and test other databases, not only Java Maven. Let me finish with some self-advertisement. If you are interested in anything that you have been seeing now, consider please running this little survey we are doing about the ethics of security. That's it, thank you.
Thank you very much. We still have some time for questions. Does someone have a question? If there are no questions, I have one. So you said that you classified the libraries for local use and intended for internet use. Can you elaborate a bit more on
yes, sure.
What the factors are?
So we have a certain database of Java Maven libraries, and the idea was to try and determine, using some reasonable criteria, let's see if it was reasonable, what was the intended purpose of that library. Because Maven has a classification in tags and also in classes, but we have looked at it and we did not understand a thing. Instead, we look at PyPy and the classifications they have there for software, and it looks very beautiful. So we thought, why don't we try to map PyPy classification to Java Maven here? That was a human-made process with different actors, and yeah, it took us a lot of time. But essentially, in the end, we have a nice classification similar to Python, and there we say, okay, look, this category of Python PyPy is internet. I think that's going to be used in the internet. Or this other one is IDEs. Well, that's probably for personal development. It can be connected to the internet, but it's more intended for the computer that is being used here. So that we will classify as local. That's essentially how we divided the two classes.
Okay, thank you. Any other questions?
Starting from his question, didn't you take into account also the criticality of the CVE? I mean, to tell us that we can use a new library earlier because different type of criticality are released later? I don't know, maybe.
Still have to.
What we use the criticality of the CVEs, so the CVSS score, was to actually filter the CVEs that we are using for the fitting. Another idea is to filter on the type of vulnerabilities you have. So you look at the exploitability submetrics, for instance, and only consider those that are, have an attack vector network or something like that. That's also something we would like to look into, yes.
Okay, thank you very much. We will now have another break, but this one will be a bit longer, and we will continue at 12:20. Thank you. Okay, welcome back everyone. Hope you're all energized after the short break. Let me introduce our next speaker, Carlo Falciola.
Hi everybody. Let's okay. Today we'll take some hints from the previous presentation that was very, very interesting and very deep and very technical in that sense. We will try to take a look of a bit wider, step back and an overview of this, of the relationship between cybersecurity and open source. Both in the sense of cybersecurity for open source and open source for cybersecurity. Let's try to do this. My name is Carlo Falciola. Yeah, sorry. I work as managing a small team of consultants in a large system integration company from Italy, that is Exprivia. And we focus on not a traditional, historical, well-known environment of cybersecurity that is more related to the defense, protection of detection of attacks, but more on the prevention and security posture management. So let's start about cybersecurity and open source. Basically, cybersecurity is a very complex task. What we are seeing this morning is just a very in-depth, but it's just partial topics on the whole world of cybersecurity. It's something that any organization, even they are developing or doing whatever, they have to care about. Cybersecurity is highly dynamic, change basically any month, and every organization has, by definition, a limited budget to devote to cybersecurity, and a part of the effort is to understand how to spend the money in order to get this kind of might that is to have the best level of protection, because you basically don't have a return on investment on cybersecurity. You cannot measure what is effective, what you did, if what you did is effective or not. You can just hope of what you get. So it's difficult. So let's go in, starting about the development of open source. So yeah, many years ago, I'm old, they were used to say, no, but there are no viruses on Linux, so who cares? No, we have just had a very good example of that the topics of managing security while developing cybersecurity application is very, very important. And there is a lot of attention has to be put on that, because basically you can write the best application, but if it's not safe, nobody will use it, or they will have to abandon it very soon. So even exactly at the same time as you care about the fact that the application that you are working on or that you are using is does not have very heavy and critical bugs, you have to care about the safeness and the security of your application. So the good news is there is plenty of tools, there is a lot of activities on that. The message in that sense that please, everybody, use it from the very beginning. We were talking about vulnerability of libraries, good. We are talking about analysis of code, dynamic or static. Please do from the first line of code that you write. Otherwise, you may end with a big amount of code, a huge amount of correction to be done, and that usually doesn't match very well with delivery dates. So in The good news is that there is an organization, OWASP, that is very, very strong on that. They can give you a lot of tools, a lot of information, a lot of strategies, etc. Please leverage these things and make it secure by design by the first day of development, or as soon as possible, anyway. And be proud to declare, because it's a strong differentiation of your initiative. If you can declare that you check, you maintain, and you produce secure code, it's important. It's important for you, for your solution, but it's also important for the movement. So that's, I mean, all the rest has been very, very well described in the past presentation. So let's go on cybersecurity and its own complexity. As I told before, there is a very high technological dynamism. The concept in that sense is that for standard software, you can think that you must be faster than your faster competitor. In cybersecurity, there is one more actor, that is the attackant, the bad people that are pushing against your solution and force you to be even faster. Please take care of that. There are so many technologies available, and they are not here because some reason. There is a valid motivation to have all this stuff around, because there are many ways to be attacked and to be damaged, and that the operation of you, of your customer, whatever it is, could be put in danger. The potential of catastrophic effects are real. It's not something that could be talking in a way hypothetical. It's real. There are events in which stuff are broken. That could be very, very big damage also to people. It's already happened that people has died because of attacks, because the informative system of an hospital got broken and some activity that was crucial for some people was not being able to be performed. So that's point. And of course, you have to find out a way to try to measure what are you doing in such a complexity. Just to give you two hints, the wideness of the market. In this case, I'm talking about the commercial market. In the commercial, just two numbers. In the States, there are 8,500 of different security software products. It's a huge amount. Probably wider than many, many other categories of software in which there is a lot of consolidation already in act. 2,800 vendors. That means a lot of complexity. Even to understand if something is completely unuseful for you. On the other side, the scenario of the cybersecurity, and in this case I land the framework of the National Institute of Science and Technology from US, that historical is the point of starting of many, many regulations, even in Italy, even in Europe, etc. They basically identify 6 main features, and we were talking about respond, detect, that's the normal stuff, but also protection, identify, understanding what you need to protect. If you don't know what you have in your organization, how can you protect? And as larger is your organization, or as teeniest are the entities that you are producing and that are digitalizing, the tallest is the problem. Because, just one word, IoT. Many small things, all of them could be in a way compromised. And so the complexity is there. I mean, 6 main functions, 23 main categories, and 108 subcategories. How can an organization cope with this level of complexity? I mean, maybe huge banks, huge government stuff could have enough people to take care of all this stuff and understand how these could cope with their own environment. But all the mid to small organizations are overwhelmed by this complexion. So it has cybersecurity an opportunity, is an opportunity for open source, or has opportunities for open source? Yes, definitely yes. There are many, because there are many topics and the coverage of the solution of cybersecurity, historically, it's pretty much vertical in some domains. And there is a lot of empty holes around this wheel. And that's something that I would like to enforce and try to better understanding and try, for example, an initiative to label, classify all the tools that are available from open source in that scenario to understand. I mean, I need to identify my asset. Okay, what can find in the open source to do that? I need to protect identity or protect privileges or protect anything else. What can find? How dare to do that? And there's a strong, very, very important activity of classification that needs to be done somehow, or start to be done. And of course, there are some area in which I think that could be a good fit. And this is the governance. The governance is popped up very recently. I mean, the sixth main function that is governed is just presented now by NIST classification. In the past was split around many others. And it's very, very focal, because it's the instrument that can you help to manage the complexity of we were talking about before. And this does not need so in-depth knowledge of cyber environment, but it needs more capability to develop good software. Good software could be good workflow or good application that can gather information from many different platforms and understand and give you the instruments to understand what is your real posture in that sense. So I think that a lot of work could be done. A lot of work is available to initiative to open source development in that sense. And a lot of things could be started very soon and will be very, very, very effective from the smallest organization to the largest one. And that's the point, because first thing is understand, then you can act. And we need definitely tools to have a better understanding of the scenarios, what we are doing. Then, of course, there is the topic of risk management. That means to measure our level of protection. And that's another tough topic in which some software will be absolutely needed. Usually risk management is used for financial topics. And in that case, financial is pretty much money. In the case of security, we are managing about probabilities. And the financial come at the very, very end of the chain. But there is a lot of work to be done before. Okay, with that, I'm almost finished. And thank you very much for your attention. And if there is any question, if there is time, I will be happy to answer.
Thank you very much, Carlo Facciola. I'm afraid we don't have any time for questions anymore. We'll take a short 5-minute break, and then we'll be back with the next talk. Thank you. Welcome back, everyone, to the Cybersecurity Track. It's my pleasure to introduce our next speaker, Ranindya Paramita.
Okay. Hi, everyone. You can call me Nanin. It's easier. So I'm from University of Trento and working with Professor Fabio Masacci. And today I will present to you my research that has been published in the Empirical Software Engineering Journal. And the title is Technical Leverage in the Python Ecosystem. So first, I want us to see that if we are as a developer, how we see the software is usually like this. Like it looks like a big rabbit that we are hopping to, and then maybe there are some vulnerability. So we need to just patch them. But this is not the reality actually, because the reality is that we are actually standing on a bunch of little rabbits, and some of them have some vulnerabilities, of course, and they bring risk to our project. And developers, they are using like a lot of free open software as building blocks. And actually, from industry, we learned that the fraction of homegrown code is as low as 5%. And dependency code is 4 times than the own code. So, okay, if this is not concerning enough for you, then I have another picture here. It's really popular. And yeah, we are actually standing on the top of a block, like a lot of blocks, small blocks. And maybe one of them is a project some random person in Nebraska has been thanklessly maintaining since 2003. So what happened if that guy just disappeared or decided not to maintain it anymore? Who knows what will happen, right? So yeah, technically our code looks like this with our own code, and there's a lot of dependency. If you were there in Carlos' presentation, this is also basically the tree in Maven, also there's in Python, also in other programming languages. So then, how do we measure the risk? We need a metric for this. So learning from finance, leverage is debt over equity. And Masacci and Pashenko in ICSI 2021 defined this metric of technical leverage, which is the ratio between others' code over your own code. So let's see how this metric is used in practice. So Masacci and Pashenko, in their research, they do a large-scale analysis on the Java ecosystem, and this is how ecosystem will like. So let's take an example. There's a small library here. It's using it has 1,000 line of codes, their own code, but the technical leverage is 400, which means they're using dependency size is like 400,000 line of codes. 400,000 line of codes. But then there's also a big library with almost 200,000 line of codes. And the technical leverage is around 7 something, so it's using around 15,000 line of codes. No, sorry, more than that. So yeah, it's 7 times of that. So they are using like a lot of libraries. But then from this, we have a question, how is the other ecosystem, like Python, for example, and Python now is growing in its popularity. And then how is the evolution of the technical leverage itself? So then what I did in my research is that we do analysis on Python ecosystem, and we see still the same trend that the small libraries is here and then going down to the right-hand corner. So what we find is that the small libraries, which has less than 100,000 line of codes, they are using, most of them using seven times their own code. So their dependency code is 7 times their own code. While the big libraries, they're using dependencies with the size of their own code. So like it's the same. So the ratio is 1. So what can we learn from here? So it's in Java, apparently Python developers also ship a lot of other people's code. And by the way, this is analysis of around 400 Python libraries with a total of more than 20,000 package version. And so what we learn from here is that understanding what else come along with your adoption of a package is essential, is the key to understand the risk that also comes with them. Because technically, the risk is uncontrollable because you cannot control whether the guy from Nebraska will maintain their code or not. So that's the first research question. And the second one is about the evolution of technical leverage. So we want to know how the technical leverage evolved during a package lifecycle. So we take a package. So for each package, we sort the package version based on the date, and then we regress the current to a pair of package version. We regress the current one to the next one, and from the regression, you can see that the technical leverage tends to stay stable. And what it means is that if you are highly leveraged, if you are using a lot of dependency, you will most likely stay doing so. If you are not highly leveraged, then you are also staying so. So what can we learn from this? So once a package has been adopted, the level of uncontrollable risk most likely doesn't change because the technical leverage stays stable. So is this a good news or a bad news? Well, technically it can be both. It can be a good news if the risk was consciously accepted in the beginning, so you know that you have this amount of risk and it stays stable. And otherwise, unfortunately, it's a bad news because if you don't consciously accept this from the beginning, at some point you will realize that, oh, I have a lot of uncontrollable risk. And so now, more deeper into the security side. So we are wondering what is the probability of getting a safe package version? If you are picking a package version, what is the probability of getting a safe package version? So of course, the intuitive way to do this, that people do in the state of the art, they are taking the number of safe version and they are divide them with the number of the total version. But this metric can be biased by the packages with a lot of package version. Because let's imagine one package with 100 of package version and all of them are vulnerable. So this package is 100% vulnerable, or it can be also 100% safe. So this one affecting the calculation in the ecosystem. Oh yeah, and this on the x-axis is the technical leverage. We group them based on technical leverage. So 0 means it has no dependency, and then small technical leverage and large technical leverage. So how can we make this metric more real? Because this is not also reflecting the reality. Why? Because developers, they don't directly pick a package version. Usually, most of the time, they will pick a package first and then take a version from the package because they will look at the functionality of the package and then decide. So then, based on that observation, we define this metric of the probability of getting a safe package version while picking a package in the ecosystem, and we find that the probability is actually higher. So the probability of getting a safe package version is actually higher than what the state of the art may be showing you. So what can we learn from this? So making statistics based on the version is good to claim that we have done a large-scale study. But apparently it's not representative to the reality of the field because the choice of the developers are usually doing the package first and then the package version. So, well, at least I have a good news here that life can be better than what researchers depicted. So, yeah. And so this is all my presentation. And if you want to contact me, feel free to scan my website. And if you have any question, I will be available to answer. And also, let me advertise this. If you didn't manage to take the QR code from Carlos' presentation, you can take this participate to this survey of do you think it is an ethical decision? And it's from our team in VU Amsterdam and University of Trento. So please participate to this survey, and I will be available to answer your questions. Thank you for your attention.
Thank you very much. Are there any questions from the audience? This one.
Hi. So you took a study that was made in Java Maven. Essentially, there was some replication in Python, if I understood correctly. Question number one, do you see any strong similarities or dissimilarities? Question number two, do you expect or do you want to do more of software environment studies similar to this? Question number three, do you expect those similarities or dissimilarities to carry on in these new studies?
Thank you for the question. So yeah, as we can see, I will show the summary. So the trend of Java versus Python, they are quite similar, I will say, this trend, even though the Java one has larger technical leverage if we see from the median. So that's answer that there's some similarity. And of course, my PhD is on this, so I will continue doing more empirical analysis on software ecosystem related to the security. And for the third one, it's actually, there's an interesting question because there's another replication study done by someone else who are also doing similarly in JavaScript. So they already did this. It's already, I think we found that in Zenodo already. Maybe it's not published yet, but it's already in Zenodo, the data. So there are someone already did this, but maybe I'm not doing technical leverage in JavaScript, but I will do more in the software supply chain security most likely because of the dependencies and everything.
Are there any other questions from the audience?
Let's assume that we have some way to measure the actual usage of the code in the library to understand if all the code that is in that library is actually used by the implementation we are looking at. Do you think this might change or as some kind of interaction of the result of your activity?
Sorry, can you repeat the
Yeah,
question?
if you can measure, hypothetically,
Yes.
but I think it's possible, to measure actually which part of the code in the library is actually used by that specific implementation.
Okay, yes.
This could help you in order to get a better aggregate of the result that you get.
Yeah, it's a good idea because I also know there are some people in, I know the team from Singapore Management University, they are doing this, that they are basically trying to find if a software is using exactly the vulnerable method to see if they are really impacted. Because for now, for my research, my assumption is that if I'm a software library, I'm using a vulnerable dependency, I'm directly vulnerable. But we know that maybe I'm using the vulnerability library, but not in the specific method that is vulnerable, and that is possible. And there are some other people already doing a research on this, and actually that can be interesting to see whether the number of vulnerability actually reduce a lot when we use this instead of the current one that I'm using here. So thank you for the question, and it can be really interesting, yes.
I have a question as well.
Yes.
So I think it's a bit similar to this question. How do you distinguish between frameworks and libraries? For example, we've seen there was a small library, but it was a Spring library. So this library probably has Spring itself as a dependency, which is huge. And but in reality, it's not really a dependency that this library uses. It's kind of an inverse dependency. Have you looked into these relations? Have you tried to filter this, or could this impact your result?
Yes, so actually what I'm doing in Python, in using PyPI, you can directly get the list of all transitive dependencies, and we are using all these transitive dependencies in our calculation. The one with you mentioned, the example of Spring, is the previous work of my colleague in Java, and what they did at that time is only a direct dependency. So it's so in Java, they only use the direct one and not using the transitive. So actually, that's also a novelty of my part, is that we are using like transitive dependencies, because still, if it is a tree and vulnerability hit you at the very bottom, it can still come to you. So yeah, we have this distinction, and we are basically calling them third-party libraries, something like this.
Okay. Thank you
For the question.
Thank you Thank you very much for your talk. We have a short break again, and in 5 minutes we'll be back. Thank you. welcome back to the Cybersecurity Track. I'd like to introduce Atao Laborero, our next speaker.
Thank you so much for the opportunity. So my name is Atao Laborero, and I'm from University of Venezia, Ca' Foscari. So here is my outline of the presentation. I will first try to motivate why exactly this research is needed. Existing authentication solutions, for example, what do we have already? Why there exist some limitations, how to mitigate those limitations. Then I will try to propose my solution. We will end up with some conclusions. Okay, so now, how many of us don't use smart devices? Is there anyone who doesn't use any smart device? No. So 61%, actually 61% own a smart device, be it a tablet, smartwatch, smartphone, Google Glasses, for example. And by 2025, 72% of all the internet users, will solely use smart devices, okay? Now, to be more specific, to be more precise, who doesn't own smartphones? Is there anyone who doesn't have a smartphone? We all use smartphones, right? So smartphones, why? Because they are extremely popular. They provide us anytime, anywhere computing, number one. Number two, they have powerful features like powerful batteries, long-lasting batteries, powerful processors, for example. And the most important thing is we use these smartphones every 6.5 minutes. So 150 times a day, we use these smartphones, for example, in shorter, in a longer, and in frequent sessions. So as a result, for example, global smartphone users increased by 49, up to 50% actually, in these 5 years of period. And the UK has now become a smartphone society. So the popularity is still on the rise. What exactly we use these smartphones for? So basically, they were developed only for communication, for example, sending voice, calling someone, receiving calls. But now we are using them for different sensitive operations. Sensitive, when I say sensitive, means we are doing transactions, we are taking pictures, taking selfies, we are sharing with our friends, colleagues, for example. And this data is very sensitive, mind you. We use these devices to actually facilitate us. They are facilitating us, but the downside is they are somehow, saving your data, your sensitive data. So a lot of personal data is actually saved and stored on your computer, on your phone. That data needs to be protected. How? How should we protect this data? What is authentication? So authentication is actually verifying the identity of a person. So I'm identified based on my badge here. This is a way of authentication. Now the point is, what do we have? We have multiple solutions like pins and passwords. How many of us use pins? How many? No. Perfect. So fingerprint, biometrics, we have these solutions. We have these options, right? And we have like different biometric modalities. Some of them, they are very useful, like fingerprint, for example, face recognition. They are very useful on these things, but some of them, they are not very useful, like palm. We cannot have iris, for example. Takes a lot of time. This part, this behavioral part is red because I'm working in this particular area. Now, for the users of pins and passwords, these pins and password-based authentication mechanisms, they are non-transparent. When I say non-transparent, it means you have to enter your PIN and password every 6.5 minutes when you are accessing your phone, right? So in this way, they are non-transparent. Number two, they could be shared, they could be forgotten. There are always some peeking eyes looking at you, what you are entering, for example. And if you are using 1, 2, 3, 4 as your password, you are not alone. 10% users, they use 1, 2, 3, 4 as the PIN on the computers, on their phones. Then we choose simple passwords, no? Why? Because simple passwords are easier to remember, but also they are easier to be broken down. So users, in fact, 67% of the users, as per this report, 67% of the users, they are not using password-based authentication mechanisms anymore. Is there any alternate? Yes, biometrics. Biometrics at least, at least provides you a flexibility not to remember something, right? So they are non-transparent as well. I told you every 6.5 minutes, I mean, this is a study. They are also non-transparent unless the fingerprint is somehow very close on a device that is makes it very, very usable, for example. And they have attack vulnerability as well. Who still thinks fingerprint sensors are not hackable? They are hackable. Why? And also, like, iris recognition is also there. Iris means this black part in my eye. This could be used as to authenticate person, okay? Now the point is Apple's iPhone 5s and Apple's iPhone 6s, they got hacked on the second day of their release by Chaos Lab Germany. So fingerprint sensors, to be honest, they are not very secure to be. And then, like, they are too time consuming as well. Like Fujisto has this iris recognition system. And you have to every 6.5 minutes, for example, you have to look exactly into the position you are required to authenticate yourself, which will take too long, for example. Also, like, maybe here you are not seeing face recognition. How many of you are biased towards face recognition? Face recognition, for example, is good biometric modality, but taking 150 times selfies is a problem, number one. Number two, privacy. So these are some concerns that my research actually tries to resolve. Anybody knows about behavioral biometrics? What exactly is behavior? The behavioral biometrics is like the identification of a person based on his actions. Okay, like how I walk is behavioral biometric. How I type, not what I type, how I type is behavioral biometric. How I speak, behavioral biometric. So these are all the behavioral modalities. They could be used to authenticate person. And they are very secure. They doesn't require any data collection, any hardware particularly, and unobtrusive data collection. Now my solution. I'm proposing a Tetra model biometric authentication solution. This solution is not, to be honest, not for just an ordinary user. When I say ordinary user who is just using smartphone for call making or call answering, no. This is for someone who actually practice security. So this solution is user-friendly. When I say user-friendly, it means it doesn't require you to remember anything. No, not at all. And it doesn't require any specific, like 5 minutes of walk to authenticate yourself, no. What it requires is, like the way you swipe on the touch screen, you see the trajectory, you have to swipe on this touch screen, which hardly requires 500 milliseconds. Then you are free to choose a combination of 4 to 8 digit free text. Free text means you could use 1, 2, 3, 4. You could use 4 zeros as your password, for example, and then write your name. All these modalities, they are very, very simple, and we are practicing them every day. Another fourth modality is hidden, which means how you are holding your phone. So you hold your phone, now you started doing all these 3 gestures. At the end of the day, you have 4 modalities to decide whether you are the person who you are claiming. Existing hardware is sufficient enough. I don't require any additional hardware. Built-in sensors, accelerometer, gyroscope, magnetometer, they are sufficient enough. Even touch screen is sufficient enough. So it utilizes the existing hardware. Then for the data collection, for example, we validate this research using a study involving real users, and we had like 3 different strategies, 3 different body postures, sitting, standing, and walking, and 20 participants actually participated in this experiment, and we conducted this experiment on S21, Samsung Galaxy S21. And you see here features extracted. So the features are, time signals that you leave your traces on the X and Y plane, for example. Then how you entered 4-digit or 6-digit or 8-digit pin, how, not what. How means how long did you press the key? How long did you press the key, and when you release it, what was exactly the time? And what exactly was the time between the 2 keys? And then you have how you hold your phone. Statistical features, very simple, and because the device this application has to run on the phone, so we have to come up with something really, really quick. And this is our approach. So we did score level fusion, all the modalities for one class classification, and then they are fused together to form a score, okay? And if the score is increased by a certain threshold, user is authenticated, otherwise no. Another problem we are facing in authentication is few samples, number of samples. Users are reluctant to provide you many samples. So we applied GAIN on the real device, on the phone, for example, to increase the number of samples. So if you are happy providing me 30, 40, 50 number of samples, then I can increase up to 100, for example, or thousands. So this is the structure of my GAIN I developed. And this is the strategy to evaluate. So first you train and test on your data, then you generate the GAIN, and then you test. This is actually the proof of the concept of our application. And the results suggest that we are already, with just 30 samples of data, we are already reaching 92.5% accuracy. And here the success metric accuracy means how accurately the classifier authenticated you. And on this part, for example, this part, you see that this accuracy actually increases when you are using increased number of samples, up to 60, let's say. So which is this, for example? So on original data, for example, this true accept rate is how many times the actual user was authenticated, 92.96. And augmented on the trending, on the increased number of samples, how many times the legitimate user was accepted, you see there is a certain increase. But the only limitation is, like, this tests were carried out only on few users. So there is still a potential we need to do. Conclusion, for example, these are just the summary of what I did. We need to involve more testers to get some concrete results, more testers, cross-vendor testing, and in multiple scenarios. Thank you.
Thank you very much.
Welcome.
We still have lots of time for questions, so if there are any questions from the audience, we can take them now. Yes, please.
First of all, very, very interesting idea. I like it very much. I have some questions about the practical implications, actually applications. How can you guarantee that, like the iris, right, the retina? I have to look at the camera. We know that that's unique per person in a sense. How can you guarantee that the way you swipe a finger in a thing is also unique per person and not an in here can also do it in the same way? And yeah, that would be the question.
Okay. Thank you very much for your interest. Now the question is how you find uniqueness in this swipe, right? So the point is, it is for sure that you are only touching those specific points mentioned as a trajectory, right? It's perfectly fine. But how much pressure you are applying? Number one, how quickly you are doing this swipe, for example, and how much size of the finger you are applying to do so. It's extremely different from person to person. That makes this modality very, very unique. And for same the case with keystrokes and with the signature as well. So everybody has different speed, different fingertip size, finger pressure, for example, applying to write something on the touch screen is extremely different. That's why it makes sense. Welcome.
Thank you. Do you have other questions?
I'm curious about how you propose your model. It's more like a multi-classification, multi-category classification, or a binary classification? Because I imagine if we put that on the phone, it's more like a binary classification, and yes or no, if the person is the owner of the phone or not. And in this case, if you calculated the precision and recall, because talking about security is interesting to see, I think, the false negatives, right? If the tool is allowing a person to access that phone or not.
Okay, thank you for asking, George. Now the question is, yes, it's a kind of a binary class classification, but it is not exactly binary class classification. I'm saying why. So in binary class classification, you are required to train your model on the samples of 2 classes at least, right? Here not is the case. So in smartphone authentication scenario, my classifier needs to be trained only on my data only. So it's a one-class classification problem. Now, when I train my model on my data, when I'm testing it on my own data, it will return me false rejections or true acceptances, right? For you, it will be false acceptances or true rejections, right? This is how we conduct methodology. This is how we conduct our experiments. I hope I answered your question. Welcome. Thank you so much.
Thank you very much, Ataula. So we'll have a short break, and then we'll have the last talk of our track today. Thank you. Okay, welcome back to the Cybersecurity Track. For our last talk, we have Georges Melegati, Moritz Mock, and Barbara Russo. Thank you.
Yes, welcome to my talk about recommending security fixes for weak open source code with AI. My name is Moritz Mock. Georges Melegati and Barbara Russo are both in the audience, and Dan will help me with the questions later on. So what I'm going to present today is the initial problem statement, the background, which will help you to better understand the overall context, the existing approach, which we did in the past, the generation of a data set, which we need for the AI tool to learn on, and our proposed solution with CodeBird, which is our deep learner. So the problem statement is that developers release code which is not perfect. In some cases, they also admit that the code is not perfect, but they also are not sure always that it's not secure. So the proposed solution is that we detect those code snippets which are not perfect, but also which are weak, to be fixed with an easy to understand solution that everyone can solve their code, and to augment the overall quality of the source code. Oops, that was true. So the background is that this concept is called the self-admitted technical debt. A developer writes a function, a class, and admits within a comment that this is not so good. This is done throughout certain patterns, most of the time, like fix me, hack, ugly solution, bad implementation, and many others. Then we try to connect those with vulnerabilities. We leverage more on the CWE, which is the Common Vulnerability Enumeration Repositories. Those repository is a collection of abstract descriptions of certain types of vulnerabilities compared to the CVE, the Common Vulnerability and Exposure Dataset, which we have seen before in the talk almost an hour ago. The difference is that one is more abstract, which we use, and the other one has concrete vulnerabilities which are in existing source code. And we use CodeBird as a pre-trained model, which we further fine-tune in a downstream task for the detection of such vulnerabilities. And here on the right, we have a nice example of a class which, with the fix me, which indicates that there is something wrong already by the developer, that he admitted that this code is not so good. Then here down, we have this memcopy function, which is called in an unsecure way. In this code snippets, there are also other vulnerability types, such that it's really something important that the developer already admitted that this should be fixed and we need to fix it. And however, he didn't mention what's the specific vulnerability in it. Therefore, our tool, which we implemented already, uses those two concepts of the SAT patterns and the CWE, connects them both using regular expressions and the SAT patterns to connect those comments, which we have seen before with code blocks, which are vulnerable. The tool looks, oh, that was too bad, no. The tool covers 34 different types of vulnerability types from the CWE. They are, again, quite abstract, and we implemented the regular expressions for those that they can be identified at line level. We used the 61 SAT patterns proposed by Border and GitHub, which initially introduced the concept of self-admitted technical debt in 2014. And at this stage, we leveraged on Chromium, such that we used Chromium to better understand if our regular expressions in fact work and if they are fine. The tools look something like this. This is the code snippet from before in red. Up there, we have the comment which is not, like is a SAT comment and indicates that the following code is not good. And here in this switch block, we have again the mem copy, but also, for example, here a missing break point or also a missing default, such that this block itself contains already a lot of different types of vulnerabilities. So with our tool, we can highlight those two different features and connect them. However, we also provided an easy-to-understand recommendation to the developers. Therefore, we used the CWE description, which is already there and widely accepted, and curated by the Mitre organization. Then the next step is the generation process of the dataset. Existing datasets have two major problems. They have tangled changes in them. Tangled changes are commits in which not only a vulnerability is fixed, but also something else. And this something else is not a vulnerability, but is labeled as a vulnerability. Therefore, the machine learner learns two different aspects, which only one of which is a vulnerability. Additionally, they are only labeled for one of the two features, either vulnerability or SAT. Our proposed data set is extracted at function level. It's annotated for SAT and vulnerabilities, and it's based on the three large open source data sets of Chromium, Mozilla Firefox, and the Linux kernel, which were already widely accepted in research. So the process looks something like the following. We start with the three data sets. We apply SOCML. SOCML is a tool which translates code into an abstract syntax tree representation from which we can extract individual features, such as in our case, the function, such that we have an entire block of XML code, which is then a function, which is retranslated back to the original code, which we have done in step 2, also with the comments. Then we applied the weak set, our tool, to these extracted functions to label them for vulnerabilities. And of course, as a last step, we applied also the SAT patterns. With that, we obtained a data set which is annotated for vulnerabilities and SAT at the same time. The resulting data set looks something like this. We have organized it in the following way, that we have the classes of SAT and vulnerable, SAT non-vulnerable, non-SAT non-vulnerable, and there is neither a SAT or a vulnerability there. One class is they're a little bit outstanding, which is the SAT and no vulnerability. Because there are so many instances in the overall data set which have at least a vulnerability or no vulnerability, so there are like a lot. So we can have there a quite high number of samples for the machine. However, in the instances of SAT, and then in the combination of vulnerability and no vulnerability, it's a little bit worse. It's worse because then the machine learner is not able to capture this idea of SAT and non-vulnerable. The proposed solution with CodeBird, which CodeBird is already a pre-trained machine learner with over 8 million data points. It's based on the state-of-the-art architecture of BERT, and CodeBird in general is already used in source code-related tasks in the machine learning. So now this is almost the same slide as before, only that we don't rely here on these regex so much anymore. We use them for the annotation, but then now we have a machine learner which produces us in an output if a function is vulnerable or not, which has the benefit that if we use a different data set, which is not annotated by us and covers different CWEs, we don't need to come up with new heuristics such that it's easier and faster to expand it in the future. So now jumping directly to the results. Here we see a single task implementation and a single task implementation for SAT and vulnerability, which means the machine learner just says if this particular function contains a SAT comment or a vulnerability. We have also the weak SAT, which is then the prediction if both are present, and the multitask SAT and vulnerability and multitask weak SAT, which means the machine learner says not only it's a SAT or vulnerability, but both informations are produced at once, such that the efficiency of the machine learning is increased. Here we can see some differences, that the single task SAT in the multitask is a little bit better, whereas the multitask vulnerability suffered by a little bit more than half a point in the F1. However, for the weak SAT, it got quite worse, and there we speculate on that it was confusing between the different classes, such that it was not completely able to distinguish them. Here, one practical example from the dataset of BigWill. BigWill is a dataset from other researchers, which is published and extracted from CVE, so from real vulnerabilities. Those vulnerabilities are then sometimes, most of the times in fact, associated with a corresponding CWE instance. This is important, as I before mentioned, that we cannot cover all types of vulnerabilities. If we can take already the work of someone else, which has an annotation for CWE, which we do not cover, it's then easier for us to come up with a new solution. So, and in particular, this vulnerability type with number 119, we do not cover. However, our machine learner was able to capture the vulnerability and label this function as vulnerable, which is a true positive in this case. And also, here, in case you're interested, you can backtrack this function with this CWE ID to the original commit and then see what the vulnerability is. To conclude my speech is that SAT blocks, in fact, contains vulnerabilities such that there is an association between self-admitted technical debt and vulnerabilities. In 2016, Gabriele Bavotta and Barbarosso found that SAT should be removed from the code base. The longer they stay, the more dangerous they are to the overall code base. And with our tool, we want to create a certain type of awareness for developers and practitioners that they fix and remove their weak code. Also, if it might not seem to be the worst part of the code, every vulnerability which is taken out is beneficial for the overall stability of the application. And as a last point, we still lack a little bit in the prediction of the recommendation for the machine learning part. And we would like to implement something similar like a GitHub action to make it actually usable to practitioners, since they might not do it manually on their machine or do not have the computational power. Or maybe, they're sometimes just lazy and forget about it, such that if it's in a GitHub action, it might be done autonomously, asynchronously in the background, and the developer only gets informed if something goes bad, else he can forget about it. With that, I would like to thank for your attention, and here in the QR code, you have the link to the application to play around a little bit with it.
Thank you very much. This was our last talk of the cybersecurity track. So we still got a minute for questions. Maybe we can go over time a bit since it's the last one. If there are any questions from the audience. Yes, in the back.
Hey, Moritz. So I saw in some of the data sets, in the training set, it already reaches 100% accuracy. And then in the validation, it reduces, and further in the prediction. So how do you, it's better if you go there, yeah. So if you see for multitask SATD and multitask vulnerability, yeah, the training set reaches 100%, so how do you know if it's not overfitting?
Yes, here in this case, it's true that it might be overfitting. However, the parameters which we have selected to train on the model is based on the application of line wool, such that we use a similar approach as they do, and therefore we have selected the same parameters to compare the applications and the approaches. As, of course, we need to invest the loss, and at a certain point, if the loss goes up again, we should stop and should not go further. That's absolutely right. However, for now, we just wanted it for the sake of comparability to have it like this, and then we need to adjust these values. Thanks a lot.
Thank you very much. Okay, I think this was the cybersecurity track. Thanks to all the speakers, thanks to the audience for the questions and for your attention.
Thanks a lot.
Bye.